Problem 1153 is a shear force bending moment diagram problem. For these types of problems, the first thing you need to do is sketch the beam. Well, that's already there in the book, and I did it ahead of time, so I wouldn't bore you with that. So the next step is to solve for the reactions of the beam. So that's, in this case, AY and ZY. So to do that, we sum the moments about point A, and they have to equal 0. And I look at all the different forces I have on the beam. In this case, an 800 Newton, 1800 Newton, 650 Newton concentrated forces, and then a distributed load of 600 Newtons per meter. So I'll look at each one of these, and I'm going to put these moments in absolute value signs. So this is actually the absolute value of 800 newtons times, it's 2 meters from AY, so it's 2 meters plus 1800 newtons times, it is 3 meters from AY. Plus 600 newtons per meter, and it is 8 meters long for this distributed load. So 8 times 600 is 4,800. And we will assume that all of that is in the center of the distributed load. This is a uniformly distributed load, so that's why we assume it's in the center. And it's 8 meters long, so that means it's right about here. Which is 2 meters from AY. And finally, the 650 Newton force. Multiplied by 8 meters. And now we just need to deal with the directions of each. The 800 Newton force is creating a counterclockwise motion around point A. To this, that's positive. The 1800 Newton force is creating a clockwise motion, which is negative. Same thing with the uniformly distributed load, clockwise, negative, and the 650 Newton force as well, clockwise, negative. Finally, we have ZY, and that's being multiplied by 6 meters. We're at least going to assume it's positive, so that would make it have a counterclockwise motion, positive. When all is said and done, we solve for ZY. In fact, I'll go with 0 equals negative 18,600 Newton meters plus ZY times 6 meters. So solving for ZY, we get 3,100 newtons. Next, take the moments about Z. They must be 0. And in a similar fashion, 800 newtons times 8 meters this time. plus 1,800 meters newtons times 3 meters plus 4,800 newtons times 4 meters plus 650 newtons times 2 meters plus AY times 6 meters. Now to get our directions, the 800 Newton force is going counterclockwise around Z, 4,800 Newton force doing the same thing around Z, and the 1,800 Newton force also around Z. So these are all counterclockwise, which makes them all positive. The 650 Newton force still creating a clockwise rotation. AY we're going to assume is positive, so it's also doing a clockwise rotation. So we put a minus sign there. So we've got 0 equals 29,700 Newton meters minus AY times 6 meters. And AY ends up 4,950 newtons. Last but not least, we must check using some of the forces in the y direction. They must be 0. So let's take all of our applied forces, 800 newtons minus 4,800 newtons minus 1,800 newtons minus 650 newtons, then add to that AY and ZY, 4,950 newtons plus 3,100 newtons and when all is said and done, 0 equals 0, and that checks out. So we'll enter our forces in here. AY 4,950 newtons and ZY 3,100 newtons. So that is the second step of the shear force diagram. Third step in the setup is to sketch vertical lines below the beam sketch for what's called critical points. So I do one on each end. I do a solid one on each end. And then anywhere there is a change in force, where a force starts or stops, I do a dashed line. I like to keep it green. Now note that I did not use the 4,800 Newton force showing here. This is merely a phantom force, only usable for the total of this distributed load, and very useful for finding the moments and the reactions, but not to be used for the actual diagrams here. So we have our vertical lines, and now we draw the horizontal axis. And we label this vertical axes. Shearing force V, and our units are in newtons. And also make sure this is 0. Did not leave myself enough space on the left-hand side. Well, now we are ready to proceed. Our rules are that we start and end at 0. So I know I'm starting at 0 here and finishing at 0 over here. And upward forces, such as our AY and ZY, will cause upward changes in the force, and downward forces, such as our loads here, will cause downward changes in the force. These concentrated loads, such as 800 newtons and the 650 and our reactions here, will cause abrupt changes in the force, very sudden, straight up. But these distributed loads will cause linear changes. If I have a force over another one, like this 1800 Newton, or even if I had another distributed load over this, you can simply add them together. So I'll just go and do this one. So we're going to start off with going from left to right, 800 newtons down. And all along the way, I'm going to note my force levels. And notice how this is down, so that means it's negative 800. Now over these next 2 meters, I'm going to be affected by the distributed load, which is 600 newtons per meter. So 600 newtons per meter times 2 meter. I'm going to go down 1,200 more. So start at negative 800, then I go down 1,200 more, so I'm at negative 2,000. Then the reaction of 4950 is here, so I'm going to go up 4950 abruptly to 2,950. Then over the next 3 meters, we go down another 600 newtons per meter. So that's a total of 1,800 newtons. So this 2,950 subtracts 1,800 newtons off of it to here for 1,150 newtons. Then at this point, we drop another 1,800 newtons. Right down here to negative 650. And then for the following 3 meters, we drop another 1,800 newtons. 3 meters times 600 newtons per meter. down to 2450. Then the reaction of 3100 newtons kicks in at this critical point, so we add 3100 newtons to here, and that is 650. And now we have no load at all here, so that means we have no change. So it's just straight across. And finally we have that last 650 Newton force, and we go down to 0 as expected. Note that whatever force we have up here, that is the slope of our line. So the slope here is 300 newtons per meter, and that's what the force is right up here. So this indicates the derivative of this. Last thing to note specifically for the shear force diagram is our maximum shearing force. Now this is the maximum absolute value, and so we actually have 2950 here. So our shear force diagram is done. Now we're not done using it because we need it for the bending moment diagram. We set up our bending moment diagram similarly, but our first step is to do the shear force diagram, which we just did. And now we also need to recognize that the bending moment diagram is based on the area of the shear force diagram. So it's the integration of the shear force diagram. The shear force diagram is therefore the derivative of the bending moment diagram. So we've completed our shear force diagram. Our next step is actually to calculate areas. And I'm going to mark the areas that we have here as 1, 2, 3, and 4. Now remember that the area for a trapezoid is equal to, in this case we've got two different heights. So we've got a base times height 1 plus height 2 over 2, essentially the average of the two heights. So the area of 1 is negative 800 newtons minus 2,000 newtons divided by 2 is 1,400 newtons times 2 meters is back to 2,800 Newton meters. But it's a negative, so I got to make sure you remember that. Area 2, 2950, remember that's positive, plus 1150 is 4,100 newtons divided by 2 is 2,050 newtons times 3. So that's a total of 6,150 Newton meters. The third area is 650 plus 2,450. Of course, these are negative, so that's 3,100. Divide by 2 is 1,550. Multiply by 3, and we have negative 4,650 Newton meters. Finally, 4 is a simple rectangle, 650 newtons tall by 2 meters wide. And that's a positive 1,300 Newton meters. We do a quick check to make sure that these add up to 0, and they do. So we continue on with actually constructing the bending moment diagram. In the same way we made the shear force axes, bring down vertical lines for the critical points. If one of our slopes had crossed the 0 line on the shear force diagram, we would have another critical point coming down. In this example, we don't have that. So I'm going to label it bending moment M, and the units are Newton meters, and I've got the horizontal axis here. Now, in this case, it's much easier to just connect the dots. So what we do is we look at each of the areas, 1, 2, 3, 4, starting at 0, just like the shear force diagram, and we go down 2800 Newton meters. So I'm just going to make a point here. Worry about the curves in between afterwards. My next point is going to be negative 2800 Newton meters plus 6150 Newton meters, which is up here 3350 Newton meters. Then I'm going to go back down 4650 Newton meters to this point, negative 1300. And last but not least, got the fourth one, which is 1300 Newton meters, which will end us at 0. Now for the curves. The curves are concave in the direction of the load. So if the load's going down for the distributed load, then the curve will face down. So it'll be concave down. So it will look like this. And even though this is a positive area, the load is still going down. So you see that the shear force is going down. So these are negative slopes, which means we will have a concave down bending moment. Now note that this changes abruptly, so this doesn't come to 0. It comes to 1150, stops, and then switches to negative 650. Goes from negative 650 to negative 2450. So that's the slope of this line right here. So this is negative 650, and this is negative 2450. This indicates the slope of the bending moment. In our last one, we have a constant value, which means that our slope here is going to be constant, and it's positive, so it's going to be going up and end at 0. Finally, we look for our maximum bending moment. So of the 2800, the 3350, and the 1300, our maximum bending moment is 3350 Newton meters. And that is problem 1153. A beam with 2 points of support and a variety of distributed and concentrated loads. First, we had to sum the moments and find the reactions. We checked with some of the forces in the y direction. Then we created our shearing force diagram, calculated the areas between the curve and the zero line, and for each of those values we were able to construct the bending moment diagram and find our maximum bending moment and maximum shearing force.